Well, thank you very much, and let me just tell you, I have absolutely a love affair with this country, as I was telling them coming in. The first talk I ever gave was at Winnipeg. That's the first time I ever gave a really talk in the Hollenbergs. That's Morley Hollenberg's father, a big family of people in medicine in Canada, had me there, and I'll never forget it. And so I've traveled in every province across here many times, and Bukowski and he had me up many times there, and so I've been here, and I thank you all very much. And I will tell you what I'm doing here. We have come here to learn, okay? And later we'll talk a little bit about that, learn from you. And so I'm not bringing coals to Newcastle. I'm going to tell you, and probably one of the best papers that I've read in a long time. I'm going to end up on that. It was from here. Dr. Wang, where are you, sir? Where are you? Right here. April the 7th, Cancer Research, 7 days old. Okay? So I'm just filling you in that I'm here to learn, not to preach, but I do preach a lot. So let's get underway. What happened, this is on the left, is a Brady Urology. Let's see, do I have a pointer up here?
Use the mouse.
What I do?
You can use the mouse.
Use the mouse, okay. See, oh, geez, don't touch anything, Coffey.
Don't pick anything.
That's right. You don't know how illiterate I am. I'm dyslexic. I haven't read 2 books. I'm really in trouble. So let me just go across here and really point to things. No, don't worry, Marty. I'd rather have you here. Oh, is that? Oh, see, Getzenberg, he always saves my life. No, I'm telling you, he's coming to the airport and dragging my suitcases at midnight. I couldn't even hardly walk with my atrial fibrillation. So anyway, let's get to business. This is the Hopkins Hospital, and this is where Osler actually lived. What do you mean lived? He lived in the hospital 4 to 5 days a week. A little different than the way it works now, right? And this is where they decided that you couldn't be married if you were in medicine, and they put you in. That's why they called it a residency, and they interned you. And so Dr. Jewett was in here for 4 months without going out this door. Dr. Jewett was one of the famous urological surgeons. So things have changed. I certainly don't work like that. Gets in at 6 every morning. So it's hard work. So this is one of the places a lot of this started. Now what happened here, 4 great doctors, one of them from Canada was Osler, and Osler came along, and Halstead, Kelly, and Welch, and they had nothing. You could be a doctor by traveling with doctors in a carriage, or you could get it at a barber shop where they were letting blood. Everybody here knows this. And so they brought these 4 great doctors together, and he said, first of all, you've got to have research. Now, that's different than what we're hearing in urology today. You got to have research, and you got to have an education, a bachelor's degree. You got to come in here. Am I talking right here?
Yeah, I'm going to make sure I turn the mic on.
Oh, sorry. I usually shout enough. They say, cut it down. Okay? So anyway, having told you that, coming down the hall was the great surgeon, Halstead. And he was flying down the hall, and this is a kid from Texas, and he'd gone to the University of Virginia, and he wasn't doing, sort of well. And he bumps into him as he comes around the corner, right up in this building right here. And his name was Hugh Hampton Young, the father of urology. And he says, Hugh! And he was so embarrassed, he knocks Halstead down practically. Halstead says, you're going to be in charge of genitourinary surgery. There was no such field, okay? And Dr. Hugh Hampton looked at him and says, Dr. Halstead, I don't know anything about genitourinary surgery. You can learn, son. Get to it. And that was the start of GU surgery. And I'm going to tell you how he operated and what he did and why that is so pertinent to what we're doing today. So he went back, and he didn't know beans about this, okay? And so he said, first of all, he'd just come back from the First World War. It was 1916 or 17. He'd been with Pershing, and he was really impressed with airplanes. So the first thing he did, he pressed to get airplanes in Baltimore, and that's why Martin Marietta has those big airships places there. He thought they had to land on water. Hugh Hampton Young. He went down and formed the Aviation Commission. He formed that big airport when you come into Baltimore. He told you got to have a big place that land planes can land. This man had vision. So what did he see when he was over there? He saw everybody in urology was dying of infections. You come in with pneumonia, syphilis, they were called clap doctors. And he said, we got to treat this. Over there at that time, they had seen that they could affect a lot of infectious diseases with mercury. So up on the top floor here, he said, we've got to do 2 things. We've got to learn to culture human cells and bacteria. We've got to make mercury compounds. We got to stop this stuff. And the first thing he did is he formed the Journal of Urology. Now imagine you're going up against the French, the German, the Brits in surgery. What is the first article in the journal? Page 1, volume 1. It was the greatest discovery of the day. 1917, gas outlets in the Brady. The first paper, page 1, volume 1, is growing human cells outside the body. Just like recombinant, not surgery. And he pointed out that you had to study how to kill bacteria versus these, how you had to develop drugs against this, and he goes on. He's not on the paper. He didn't put his name on the paper. In fact, the Japanese postdocs, the first one on there, and some other people on there, and that's it. That's volume 1, page 1, Journal of Urology, 1917. Then he formed the Urological Institute. Well, the first thing he said is, we got to have chemists. So he put these chemists upstairs, and he started making mercury compounds. They titrated them against the bacteria. They titrated them against the cells, and he came up with one. Did he form a company? No. He gave it to the world. It's called mercurochrome. Mercurochrome was discovered in this building by Hugh Hampton Young's chemistry lab on the top floor. He said, we got to have engineers. And so he goes out and gets all these optical engineers how to look into the prostate. And every day he operates, he has an artist in the operating room, has an engineer in there trying to figure out better instruments. He comes up with a cold punch, does BPH on that, and right away, bang, we're on our way. He gets Diamond Jim Brady. He fixes up his prostate so the retention goes away, and he becomes world famous. He never stopped engineering. He never stopped chemistry. Guess what else he did? You got to go read these articles. They're stunning. Next thing he did while he was over in Paris is he held radium. He'd never heard of radium. Madame Curie, radium. He spent his own money and bought a block of radium and put it in the desk behind his office. He should have been sterile from this. I mean, you cannot believe how much radium he put in there. And he made needles out of it. 1917, page 525 of volume 1. He stuck the needles into the prostate. And he says, here's the dose response curve. You got to put this radium into the prostate and into the bladder cancer. And he has 63 patients treated with brachytherapy in 1917. And he concludes, this doesn't work very well. But he points up, it kills the cancer, but it's got to be worked on. Then he thought, boy, wouldn't it be good, because Hunter and these people had shown that if you castrate animals, the prostate shrinks. So he castrated 7 patients with prostate cancer. And they got up and walked. Then they came back and died. And so he wrote in this old journal that castration of the prostate isn't the answer because it becomes resistant to it. Then Hopkins came in 45, you know the rest of it. 42 got the Nobel Prize for doing it again. He claimed it was a cure. It ain't a cure. Okay? They come back and get you. Okay? So I'm just trying to picture for you how this actually developed. A ton of these things. Now let's pick up Don Coffey. He's a little guy walking up the road. He comes in. What does he want to do? Is cancer research. Hillbilly from Bristol, Tennessee. He can barely speak English. He comes in here. There's tons of little kids going up and down the elevator with him every day, dying. Every time they left the playground in 90 days, they were in a coffin. They had ALL. They don't die like that anymore. I have no idea why that works. I know all about skipper models. I cannot tell you why that works. And then the other thing that went up and down the elevator was the number one killer of young males. Cancer. It was testicular cancer. And when they came in, they're dead. Their lungs fill up, they're dead. Now they don't. Now they don't. Do you know how that works? I don't know how that works. That's why we're here. Getzenberg is a PI with Ted DeWeese. They're going to try to find out how that works. We think it's got a lot to do with something going on here by a man named Marty Gleave and heat shock proteins and a lot of stuff. We're here to learn, folks, okay? And we think this is absolutely critical. Then I ran into this guy back here, sitting back here, named Nick Brukovsky. Now, Nick was out of Russia, and so was one of my postdocs. He comes from nobility in Russia. That's why I was trying to get everybody set up there. And he came down there, and he figured up something called 5-alpha reductases and all this stuff. And did they treat you very well? They smacked him around. He got so mad he went to Europe and got on a motorcycle. Didn't you ride around a little bit over there in Europe or someplace and took a year off and then came back and decided he wanted to do this. Then he came up with intermittent, and you all know that. This place put that on the map. And we're still fighting over androgen withdrawal. We're still fighting over intermittent. We're still fighting over radiotherapy. This goes on and on and on. But the people are getting up and walking away. We do not see advanced cancer. Now I'm going to tell you one that is one of the greatest discoveries I ever saw. In walked a guy into the building. He was a medical student. And he cleared out the hospital of urology. So let me tell you about what I mean by clearing out. The number one surgery going on to the Johns Hopkins when I arrived in the door was what? Ulcers. Taking out stomachs for ulcers. Why did they stop doing that? Nobody ever told you, did they? Because they found that there was a receptor called histamine 1 and histamine 2. And if they could put something in there and get that and stop ulcers. And Tagamet. Boxcar loads of Tagamets were sold in the United States. They don't do that anymore, do they? Why? Nobel Prize given later, Helicobacter, right? Is anything like that going on in your... You bet there is. And that's one of the things we're going to end up on. And so it's not that surgery was wrong for ulcers. It was that you have to go to the next step. And it doesn't kill surgery in medicine. So what got changed in medicine here was two things in urology. Number one, the number one bread and butter of urology was evaporated. Evaporated by a resident working in this building. And number two, okay, a disease that we never saw became one of the paramount diseases. We didn't know it was there. And now that's treated. We're going to show you what those two are. So the first guy to walk in the door was this young kid. First of all was this young man, Walsh, and he says, "Hey, Don," he says, "how do you get what are the nerves that cause erections?" I said, "I'm sure the Germans worked that out in 1820. Let me get a book. I'll get it for you. Get back to you in a little while." It isn't there. There's no nerves for causing erection. Jeez. And I said, "What?" Now, here's the secret for every young person. If this is true, what does it apply? He operated on a few patients, and they had erections. 99% of them did not. He said, "How does 1% do that?" And he began, the rest of the story. He did nerve sparing. Well, he also found you could stop the bleeding, and that was Walsh, and he didn't work on that stuff. He worked on descending testes and external genitalia. That's what he came here to do. He came up from down at Wilson's operation, same place Prokofsky came up from. And he went down to get the androgen receptor, Walsh did. And he couldn't get it. He worked and worked and worked and couldn't get the androgen receptor out. It was a failure. But he discovered something that's been totally ignored I want to talk to you about. He found that if you took and castrated a prostate, boom, in a dog, he'd go down to here, castrate the animal, give back testosterone, comes right back. Give back dihydrotestosterone, it comes right back. Give testosterone and estrogens, it still comes back. You do not block androgens with estrogens. So T&E, it comes right back again. If you give DHT&E, it's 4 times bigger, so it goes from there to that, and it's all DNA, and it's hyperplasia. Estrogens promote dihydrotestosterone stimulation of the prostate and make it hyperplastic, and I have no idea after 25 years why that's so. That's the heart of what estrogens are doing, something very big here. T&E doesn't do that. So when T goes to DHT, as Prokofsky will tell you, that's an irreversible reaction. T goes to DHT, it can't go back. But T goes to estrogen. I mean, this is such an interesting, complicated story for urologists to figure out. So let me go on with this story, and you can see how we're thinking about this and doing science here. And this young guy, next young guy to walk in, is a medical student, second year medical. He said, "Dr. Coffey, I'd like to work on the pharmacology of the pelvis." I said, "For what?" He says, "Well, I think we have to know about drugs that affect down where urologists are." I said, "Get some sleep and a beer and start over tomorrow." Well, he comes back around and you let them do what they want to do. And I said, "What do you want to do?" He says, "Well, I'd still like to do that." I said, "You know any Now, I had been acting chairman of pharmacology at Hopkins. I don't know any pharmacology. You kidding me? And so I said, "What are you interested in?" He says, "There's different things that block those nerves." I said, "Name 2. He said, "Well, there's alpha blockers." I hate that stuff. Alpha blockers. I said, "Okay." I said, "Let me go. I'll go over and buy a book." I give it to him. I said, "Read this book. If you still like it, we're going to get behind you and do everything." His name, Herb Laporte. He comes back with Hytrin, which had been looked at by the Israelis and people, and he put 90% of the operations in this building when I arrived were for benign prostatic hyperplasia. And when I said there was no progress, they cheered at the AUA because that was their money maker. That was 90% of their money was made by doing TERPs and this. We don't do those anymore. We don't castrate for prostate cancer. This was all we did back then. And he came up with alpha blockers. He knew nothing about it. And I think that's the biggest breakthrough in American medicine. 1 out of 4 men have to be treated for this. And here's a urologist who freedom of surgeons don't like that, so they don't even bow to him. They say, oh, yeah, that's that damn poor up at NYU. Yeah, get him out of here, you know. So I'm serious. You see what I'm getting at? So I want all young people to realize this. Then the next guy walked in. He's an African American. He walks in. He says, I said, what do you want to work on, kid? You have to work in the lab. He says, I want to work on African American disease. I said, name 2. He said, sickle cell anemia. I said, great. What do you want to do? He said, they can't get erections very well. I said, we know what that is. He said, what is it? Red blood cells don't bend right when they go through. You know all the standard textbook stuff. He said, I'd like to find a way to stop that. And I said, well, and I said, I don't know anything about that, but go, it's like Herb Laporte, get on it. Next day he went to a talk. Nobody had ever heard of this compound except one of our residents named Jake Rafer, coming back from UCLA, gave a talk about nitric oxide. And this young kid walked in, and his name was Bud Burnett, an African-American surgeon, which we never had at Hopkins because they didn't allow African-Americans. We had separated the bodies in the morgue, and I won't even go on to how bad things were with scholars on board. But anyway, what he did, he comes along, and he starts wanting to see if this nitric oxide does it. And I said, well, nitric oxide's laughing gas, isn't it? I mean, what's nitric oxide? What's nitrous, nitric, thiocid? I don't know these compounds. I'm a chemist. He gives me a lecture on nitrogen. It has 7 valence states. It was the most interesting lecture you could imagine. I learned more about nitrogen. And the next thing you know, he's got the cover of Science, first author on the paper, showing that nitric oxide is a way that erections work in humans. Now, meanwhile, Pfizer's got their drug. They're off and running. They didn't know enough about, but they could see right away how this could be an important drug, heart drug they had, and Viagra, Rista. We didn't even have people lined up here being treated for erectile dysfunction. We didn't even know it existed. Now, it is the number one thing on television, every NASCAR race and NFL football game is, hey, we can stop this. Okay, now I'm going to show you what the problem is. Jeez. Here's the problem. HIV. How many papers on HIV? Well, if you go out there and look at it, there's 197,138 papers published in PubMed on HIV. How many on breast cancer? Breast cancer. 115,012. How many on prostate cancer? 42,290. I haven't even read 290 of those damn things. Okay? How many on bladder cancer? Man, how many world authorities are there on bladder? We don't have many. 14,781. BPH. 1 out of 4 males, 7,433. How many on prostatitis? The big one that a lot of people have to go see their doctor about. Nobody likes to treat it. 4,826. Now listen to this. The one we know the most about is renal cancer, isn't it? We can do all the molecular aspects of that almost, can't we? 3,700 papers. What about testicular cancer? We can cure that. Lance Armstrong has mets the size of golf balls in his brain. We cure that. 3,700 papers. Jeez, there's no. How many in all of urology? I think it's 92,000 or something like that. What I'm trying to tell the young people here, all the breakthroughs in these things came from urology departments. PSA came from people led by urologists. PSMA, LNCAP cells, biopsy guns, transurethral resections, blocking erectile dysfunction. You are responsible for this field. Hugh Hampton Young understood it, and the journal Urology decided to be a total surgical journal and took out all the science. They got rid of residents doing research, and just a few great meccas like this place, ours, and some others are left trying to carry this ball. You all are really making great progress, and I'm not here to make you happy. So let's get started. We're going to take off 100 miles an hour. I'm going to blur your mind with slides. You're going to get phototropic seizures, and I'm going to try to get you out of there. The rest of this is just a lot of who shot John about where we are. The first thing I'm going to tell you is that cancer of the prostate rises to the 6th power. You have no idea what's getting ready to happen. Why? You have no idea. Oops. There we go. I got it figured out. Look at that. This is the most amazing slide that I've ever seen in medicine. I'm going to let you read it. What they're doing here is they're taking the country with the longest life expectancy of the 20 or 30 top countries with superb records. And they're saying, okay, how long does the longest country live each year? Can you believe this, ladies and gentlemen? This is a correlation coefficient of 0.98. I don't see that in biology. There's 140 points on here. It goes back to the earliest records. This is the male on the blue. And here is the female. Now, if I say if this is true, what does it apply? I'm going to give you a couple. Why does the female higher than the male? Where are autoimmune diseases more in the female? Does the female have DHT and E? Yes. To make PSA? Yes. It's all very similar. We don't know what estrogens are doing. But that's not what I'm here to yell about. I'm here to show you that when my father died at 61 years of age here, in the 40s, okay. In fact, in 1950, the average life expectancy in the United States was 96.8. We heard this was going to plateau. Everybody was going to reach a certain age. No, it didn't happen. It didn't happen. We got fooled. Where's it going to plateau? I don't know. But every 4 years, we extend life expectancy. So what do we got? We got all these people that were dying at 65, and we set up all the rules of retirement and everything. And now we're sailing up this line every 4 years, grabbing a year. What's this going to do to BPH? What's this going to do to cancer? What's it going to do to lower tract infections in females, which we know nothing about? Okay? Really. We got big time work to be done in the field of urology. Don't you think for a minute we don't. This is happening all over. In fact, these Leistmans up there, all in Japan, who has the best records later. But it's going up like a shot. And this science article says, wait, we missed the boat here. Is that an amazing? Wouldn't you think there had been Larry, wouldn't you thought there had been an inflection in here for penicillin? There had been something in here for something? What about DNA? No inflection for anything. This is part of evolution. This is part of what we're doing with tech. Where does this back extrapolate to? I could write papers just thinking about this grade. Pretty depressing. So Hopkins comes, this is all cancers now in the United States. Look at this. This is the war on cancer. This is the mortality rate, the died. We're not talking about diagnostic problems, seeing your doctor. We're talking about in the coffin, dead of cancer with a thing that says you died of cancer. Are we making progress? So here we made our big molecular biology, and we're all excited, and I'm excited about it. But it didn't do much, did it? This is 1983. Bob Weinberg comes to Baltimore. The cell biology meetings and shows that it's a mutation of the 12th amino acid. The 12th amino acid of RAS is discovered here. It didn't do squat. It didn't do what Herb Laporte did. It didn't do what our friend Bud Burnett, Arthur Burnett, did with with erections and stuff. And it doesn't mean it's not important. I think this is important. It's not the way you're telling it to the people. It's not. Oh, we did the human genome. Oh, you did 5% of the human genome and said you did the whole thing. Because 95% of it didn't read out. Okay, let's keep going here. Got that? Now I'm going to show you what was discovered in this period of time which didn't do much to this, and I'm for this, don't get me wrong, but it's not as simple as we tell it. This is what happened in those last 27 years, 26 years. We got 131 new drugs through the FDA. Boy, that's hard to do, isn't it? Oh, darn it. What am I doing? We'll fall asleep on this thing if I don't get it straightened out. Oh, dang on. How do I back this up? There we go. Oh, I've got to back this up. How do I back it up? There we are. 131 new drugs. Didn't beat that curve. Oh, yeah, we got some Taxotere. We got a little stuff here, right? Yeah, come on. We got a new androgen blocker. No, come on. We got to get out of here. We got 44 oncogenes. We got 40 suppressors. We got 40 tempers too. We got stuff. Keep working, folks. We're going to figure it out. But it's not as easy as we're trying to play it is. Why isn't it easy? And that's what we're doing up here visiting with you. Is there a common denominator to cancer? Yeah. What is the common denominator? Listen to this. This is the way I operate. I have actually 5 professorships and never had a course in any. I was never trained as an engineer. I lied to you. I was trained, I don't know what I was trained in. But I can tell you from East Tennessee State, Phil, and everything, what I did is I became the head of an engineering operation at Westinghouse with no degree in engineering. I became the head of the second largest clinical department as an acting director of the Cancer Center with a Ph.D. in 1987 for a year and a half with no M.D. You don't have to have M.D.s to do this. You have to care for patients, talk to the orderlies, talk to the nurses, get out there and do some serious thinking. And so there's common denominators. What are they? You can look at a cell and tell me it's cancer. Excuse me? You can look at a cell and tell me it's cancer? Getzenberg's going to tell you about that. Yeah, just hand me a cell. And I said, oh, I don't need to do anything but my eyes. That was known in the 18, and it's true for all cancers. It's pathologically confirmed. See what I'm getting at? And if it's not cancer. So that's what we're after. So this is the whole heart of the thing. It is evolution is what's been turned loose here. And you're not going to beat this playing around, okay? And let's see what it's about. Folks, evolution is the most amazing thing. Read that. Can you imagine surviving by selecting an animal that's running through the woods with a rack on top of its head? Who made up that damn system? Who decided to put the testes down here where they're not protecting your sliding down barbed trees when you're a primate in the jungle? This is not smart. Somebody's screwing up. It works. If it doesn't work, it wouldn't have been selected for 3.5. Why do you think this falls off? What makes that big things fall off? Does anybody here know? What? Come on, Bukowski, wake up back here. What makes those things fall off? What? Sure, but what sets it off? No, I'm just showing you we don't know anything. We don't know what the seminal vesicles do. Light. What do you mean light? If you put them in a cold place, they fall off. Geez, we got a lot to learn. And here's what evolution's about. Now, these are Mickey Mouse slides, but they make big points, folks. This thing has been living in Siberia for years without change. Why? It was selected to live in Siberia. If you go back 1 million years later, it looks like this. Ready? If you take all the babies from this wolf and stick them in a box and say those are the little wolfies, and you keep breeding them, you get this. Are you kidding me? If you take all the big wolves and you put them in, you get this. But if you left the wolf there, you get this. Is that mutating this wolf? No. What's it selecting a winner? This is what's happening in cancer. You can come up with a better chihuahua drug, but then this one comes out. See where we're going? Now, you may live long enough you don't die of it, okay? You die with it. That's another argument. Everything in this planet which was selected by nature is now selected by you. What do you mean? Walk in the grocery store. You selected tomatoes, the corn, the lettuce, the celery. There's nothing in the grocery. The bulls, the cows, the chickens. You selected everything in the grocery store. In fact, you walk down the aisle of that grocery store 20 years ago, everything had sugar in it. There's no sugar there anymore. Why not? Because we're using corn syrup, fructose corn syrup. There's no sugar in the Iola anymore. These things are being selected. Cows are not, and cattle are not bred and raised the same way they were 25 years ago in the United States and in Canada. We now feed them in corrals with corn, you know the stuff. It's a different ball game. We're selecting. We don't like the flowers. We don't like the bushes. We change the grass. We select everything. Show me something we haven't selected. So we select, okay? And when we select it, we can find something that marks what's in here. And it's not as much as you think it is. It's some simple genes sometimes. And that's what happens. And it doesn't matter whether you're using, and here, MDR, Victor Ling, you know the whole study, pea protein, it doesn't matter what it is. It'll select already existed methotrexate resistant cells in there, just like the chihuahuas in there, and it selects it out. So, can you have a prostate cancer without an androgen receptor in it? You bet you can. PC3 is one of them. Does the normal prostate of a human grow by making its own androgen? Absolutely not. You can castrate a dog, a rat, and the prostate will shrink to nothing and stay like that forever. Now, cancer has found a way to beat that, and it'll amplify its gene. It'll change anything it can, and y'all are experts in this and had lots of talks on this here. Very important. But you're beating that system. And that's it. It's that the corn that's your normal prostate has all yellow seeds on it. But you put one yellow seed in, you grow up this thing, and Barbara McClintock thought that was very interesting, how you could have one seed make so many different seeds. Didn't make sense in genetics. Nobody was interested. She won a Nobel Prize. And guess what it was? Jumping genes. And guess what she saw? Her eye through the microscope saw the chromosomes jumping like TMPRSS2 and all these things. And she went out and said, hey, there's some jumping genes here. There's some transpose. You know what the major DNA is in your body right now? Transposable elements, one of them. ALU sequences. What do they do? I don't know. Nobody knows. We have a big talk on transposable elements in human genetics. Tons of your DNA is transposable elements, repetitive sequences, things picked up from bacteria and viruses. It's not the simple story that they made out to be when Darwin told it. Darwin was a genius, but he missed this, okay? And here's some of the way it happens. It knows how to self-organize and information transfer, but it's a chemomechanical engine. This is what Wang's doing right here. What he's doing, he's looking at live cells. All of pathology looks at dead cells. People look at cultures. This is not what's going on inside the animal. And you got to work with how the live cell responds. And he did. What did you discover, sir? I'll tell you. It was April 17th, cancer research. He took some bone stuff. He got some juice off the bone, put it on those cancer cells, and they changed the cancer cell to become androgen insensitive. And they also changed them to grow differently. And then there's a guy named, Leland Chung and all the people in this room, they found out that the bone's talking to the cancer's talking to the bone. This is not a simple story. And it's a very interesting story. The environment talks to the wolf. This was known all the way back to Bavaria. Something's wrong. What causes this? Is this a mutation? Probably, but something's wrong with that chemomechanical engine. What chemomechanical engine? That thing knows how to separate these 23 chromosomes. And let me tell you, this little piece of DNA here, if that DNA was pulled out of that chromosome, it would extend 12,400 times longer than that piece of chromosome. That wire is wound up in here. It's topology. It isn't just sequence. It's topology. You got to shrink the DNA 12,400 to get it in here, and then never get them entangled, and they're unwinding each little replicon at 100 RPM. This is a topological problem like you cannot believe. That's why we're into physics. And so there it is. And here's the first thing we discovered. We didn't discover this. We worked on it. And the guy from Kyoto from Osaka worked with us on this, named Takaha. And what happens is these are the cancers you can cure. the 922, the 814, the Gleevec, all that. This is what happens not in prostate cancer, in the one that kills you. The cancers that kill you, that's only a small percent of the cancers, that's the only ones we're interested in, are these. And so I went to Mary Claire King. I said, Mary Claire King, when you look at metastatic lesions in patients that are in the coffin, what do they? She said, they look like that. Guess what? LNCAP looks like this. PC3 looks like that. We say, oh, they're both prostate cancer. Just a moment. So here we are. Take a look at this. This is 23 chromosomes from the PC3. This is Takahata's paper when he did this, and other people have done this. And Billy Isaacs and some other people looked at the genome, comparative genome hybridization in human prostate cancer from 23 consecutive people who died as warm autopsies. They were worse than this. They were worse than this. 85% of them had lost the 8P arms. Big chunks of DNA are lost. And the 8Q, they're gained. What's the 8Q? Well, now we know 8Q24 is somewhere down around MYC. It isn't MYC, but it's in that all that repetitive sequence around there. There's a whole world to be worked out here, and we're making it just too damn simple. So these are 31 unbalanced rearrangements. There are no unbalanced ones up here in the LNC. There are 4 up here of balanced. There's no balanced rearrangements here. We could put in high mobility group proteins and change this into this. The chromosome topology and organization, and now we got tempers too and all that. Now take a look at this. It's 2008, a few months ago, November. And this is Eric Lander, the biggest guy in the field. And this is a chromosome. And he's only going to look at this little teeny piece right here that you can't even see. It represents 0.01% of this chromosome. And he's going to run this out for different patients. Folks, this thing is complicated. This is a small nucleotide polymorphisms, the sequence changes. It is incredibly, in this little area, complicated from patient to patient. So which one of these decides what's going to happen? So let's go to the next one. So here is where Getzenberg's going to come talk to you and where we're going to try to get some help here. You got the code. The code is inert as these little things are in a grocery store, but they carry information. And when you hit this, it says celery, bought in the 18th of March. It cost this much money. We got it from California. All the information is in this little barcode, but you got to read it. If you don't have the scanner, if you don't have the nucleus, you can sequence this forever. But to get it into information, you got to run it through a scanner. This turns out to be, it's just look at how this works. Remember, we only need 10 numbers. That's 410-337-9283. That phone number can get anybody in the United States whose name's Wallace Coffey, my brother, because it doesn't take many numbers in a row to pick out 10 numbers. I can get anybody on a telephone, on your cell phone. So how many numbers? There's 3 billion of these things. So here's the difference right here between a human, a chimp, and cytochrome C oxidase. Now, how many of these little lines are there in cytochrome C oxidase? There's 360 of these codes in there. What if you just take these right here, just 17 of them, you don't have to take all of them, and see how they're different. This is a human, this is a chimpanzee, this is a gorilla. We don't even need to see the animal. We can tell you every type of butterfly, snake, just by scanning the code, the barcodes. And that's all Scientific American, and you know that. And so you can pick one gene from 20,000 genes real quick, and you can find this. This is personalized medicine. But it's not going to be that simple. Guess what? You do this one over here, you can tell me it's celery, and you can tell me exactly what grocery store sold it to. This is precise stuff. But you better have a scanner, and that's what we're not working on. And this is what we think is changed, and when you see the scanner change, it's cancer. Now look at this. Now, Wang, this is like what you did, only you stressed a cell. What they did here, and this again is 2008, cell Nature Reviews Molecular. What they did, they went in and took one of the great guardian angels of the cell, P53. You know about that. You stress it. You look at it cross-eyed, and this thing is the police force of the cell, and it runs in there to protect things. So what happens if you take a live cell and stress it with different things? How does P53 change the way what he did, Wang did here? He took extract from bone and saw how it changed it. Okay, now they're going to do it a little different, and here's the way they do it. They're going to look at the proteins, not the sequence, how those proteins are turned on and off. And here it is. Amazing paper, okay? P53 is the guardian angel. You damage that DNA, P53, the police force rolls out. Over here, you heat stress it. That's what we're doing, and we'll be up here talking all these heat stress things that are done here by Marty Gleave, and it does things. Metabolic stress does things. And so what does it do to the level of these? They can put them up here in bars, just like you do the barcode, and they can look at how these things are affected by that. You can look at whether they're in the mitochondria. These things are going into different compartments in the cell, the mitochondria side. You can look at how they modify the histones, whether it's acetylate, sumolation, methylation, ubiquination. It's not just acetylation, it's a whole bunch of things. Then you go over here, look at the cofactors, P300. And you can come across here and find a pattern for apoptosis, cell cycle arrest, autophagy, DNA repair, senescence, metabolic rate, and embryo regulation. The cancer moves back to the embryo. There is a lot to be looked at in the dynamics of this cell. This is not DNA sequence. This is how the cell is responding to these stresses. And so if the cancer goes to the bone, how does the osteoblast respond to hit the prostate? Why did you say it made him androgen insensitive? Yeah, he had some of that in there, right? Now, it's not going to be as easy as just tell me what your DNA is now, because you won't even have a winning bet on that in identical twins. If I have identical twins here and one of them gets prostate cancer and we can do personalized medicine, the other one should do it, shouldn't they? No, less than. You won't even have a winning. 42% is the highest of any cancer that's prostate. You got a 42% chance if you know the exact sequence of every SNP and everything in these identical twins. So what determines it? It's acquired. Most cancers are acquired, and that we can't put in. And once you have cancer, I do not want to know that you can tell me I got cancer. That is the most useless information you can give a patient. What I want to know is I got a killing cancer on board. How soon is it killing? Well, when Brukovsky and Marty McLaughlin, we thought that the cancer changed and got worse. Not like that. You do an experiment. It turns out the kitty cats were kitty cats way out. And the bad ones were bad before you could ever see them. What does that mean? And here it is. Geez, there's all these different cancers in there. Which ones you going to... Boy, I tell you, we spent time with Gleason. He came down and spent time in our lab with us. He said all I was trying to do was standardize it for the Veterans Administration with a drawing. And as soon as Hopkins had one good, medium, and poorly differentiated, MD Anderson had 1, 2, 3, I thought maybe I could spread it out to 5, and I did. And then somebody walked in, but what if you got one with this in it and one with... How do you handle that? And I put them together. He said, I never intended this to be continuous and all that stuff. But we did. We go ahead and we act like we know what we're doing. We don't know what we're doing. And here's the question. If I got number 1, I need to know it. If I got number 2, I can't find a cancer, but that prostate's going to make kitty cats. And if I got number 3, they're going to make tigers. And if I got number, it's going to make inflammation and BPH. Can you look at the prostate before it goes sour and tell me that? Can you do it with the bladder? Larry, can you do it with the bladder? But you go in there and look at an unstable bladder, you got troubles, don't you? Yeah. Okay. Now, you're not going to take things out, but if you could tell me this patient's going to die of this, can that happen? Well, a very smart young man who dealt with this looked at this. Now, we're going to go off here in a minute, and I'm not going to handle any questions here, Larry, because I've told you more than I know now, and half of this is wrong. Okay, and so what I thought I'd do to help you out is I sent Scardino down. He'll be down in a few weeks. I called him up. Go up there and clean it up after I mess it up. No, I noticed you have him on the schedule here, Scardino. So here we go. Look at this. This blew my mind. If you double one cell 32 times, you get 1 billion cells. Let me repeat that. You double one cell, the number 1, and you go to your calculator and you double 1. 1, 2, 4, 8, 6. You do that 30 times, you have 1 billion on your calculator. I can't believe that. Just 30 times I double the number 1? Yeah. See how it works? And Skipper came up with that. And then Isaacs and a bunch of us went after this way back. And here it is, 1 doubling, 2 doubles. This number says 1, 2, 4, 8, 16. And so if you do that, it goes out the top of this building. This is velocity. Just think about PSA when it's doing this. People don't think about what this is really measuring velocity. Now, if you take this very same data and make a log, it's a straight line. So if I have 10 cells, and they're doubling every 2 days, and I have 1 million cells, and they're doubling every 2 days, I have the same doubling time. It's not the same tumor, 10 and 1 million, is it? But what about the velocity? Well, it'll reflect in the velocity. It won't reflect in this. This has to be thought about. This is not as simple as the story is being. But this is the best way to look at this problem. Not a static picture. A static PSA is essentially useless. Because if you tell me it's doing that or that, that's a different. Now, who did this? Now Carter says, hey, he said, what we could do is we could go get all the PSA values, not from a screen, from going to the population of East Baltimore where the Aging Institute, has saved the samples for thousands of samples for years, every 6 months. They go in and they're frozen. Let's see if it's stable. It's stable. So he goes in on the same day, on the same time, and assays this patient's longitudinal and sees whether they died of cancer or not. That's the best study you'll ever do, because that's not somebody going to see a urologist because they're having trouble getting up or their wife thinks they need to be looked at. It's taking just a population in the neighborhood, paying them money to give me a vial of blood, and then seeing what happens. And this is the famous thing he reported. Now remember, this was in 1992. This is a normal level of 4. Bill Bonner did that. And look what happened as he followed out for 20 years. These are the ones that nothing happened to. These got BPH. These died and got prostate cancer, and it's metastatic. What does this mean? Well, how do you do this? I'm going to tell you right now, this is one of the best indicators if the prostate isn't changing. But if these cells are progressing, they would get a different slope. They wouldn't have the same slope, but they have the same slopes. And this has been checked now. It's called velocity. And nobody paid any attention to this. I can tell you right now, don't go just take my PSA tomorrow and tell me, oh, it's going up and all that. You got to get a little bit more information. How soon do you have to get it? Big papers are getting ready to come. D'Amico came down to Baltimore. We showed him this data. We showed him all this. He said, I can go do that. He did it. It works on his radiation patients. Then in comes Catalona. Now tons of people say it doesn't work. Let me tell you, when you take this way out, let me show what happens. Never mind. It flattens out. This gets Gompertzian kinetics, very complicated. This is the point you got to know. And that's what we haven't worked out. But it's being worked out. The papers are coming. Now we got to go off the air. We got very fast. Here's what I want to leave you with. I love this picture. It's my favorite picture. Okay. That this is the DNA that you're born with. That's what you inherit. This is what you acquire as you live. This is as important as this is. And this is the SNPs and the inheritance and whether your father has it and the genes. These are very important, okay? But they're not any more important than this is. Why aren't they any more important? Because prostate and breast are similar. What are they similar for? Those things at the bottom change them. Here they are. Look at this. Take this to the bank. This is the instance of prostate cancer and breast cancer. You can line up any cancer you want to. They do not go hand in hand except breast and prostate. And they do in every country. And if these people right here move to here, it goes up. Did you change their DNA? I don't think so. What is this? Methylation patterns, inflammation. What do you mean? Hey, that sounds like what happened in the stomach. What do you mean inflammation? I don't know what I mean. I mean there's all these macrophages and nitric oxide and stuff. Big time stuff. You know this. Everybody in this room knows this. That doesn't sound like, it sounds like something else is going on here. And I'm going to bore you with this, but the first thing is I used to go into the laboratory when Coffey was in the lab and I was in the lab. And I'd say to people, I'll give you $100 if you can make prostate cancer in a rat. You can sew methylclanthine sutures in, you can turn on and off the growth, you can feed them anything you want to. I'll give you $100 if you walk in. Wilhelmine Dunning looked at the pedigree of 3,327 rats and never saw, a whole families, not just rats, never saw prostate. There's no animal ever died in a zoo of prostate cancer. London Zoo, Baltimore Zoo, Philadelphia Zoo, none have ever died except the dog. Geez, don't they age? Don't they? What's going on here? Well, it turns out that the difference in these countries is a lot of difference. You don't see cheese in Chinese restaurants. You ever seen a piece of cheese in a Chinese restaurant? Ever seen a piece of cheese in a Korean restaurant? In a Thai restaurant? You never see it. In the United States, we put cheese on ice cream. We put cheese on everything. Do the Chinese have lactose? Yeah. Do they eat pizza when they? Yeah, they eat pizza. So, but look at this. When you burn meat and you feed it to a rat, you get prostate cancer. And that's been worked out. You have to have inflammation. The seminal vesicles, only been 40 cases of seminal vesicle cancer. They don't convert this to a carcinogen. Is this the answer? No, but this is a serious problem. Serious problem, okay? And here, remember I told you about the gut, about the Helicobacter? Look at that. Most of the genome in you is not in your DNA. It's in this 30 different floras in your mouth, between the teeth and the roof and the back, totally different. They metabolize carcinogens. They work totally different, and some of them are not harmful. All are essential. And here comes why we can't duplicate these things. If you eat soy, whether it gets made into phytoestrogen or not is totally dependent on the bacteria in your stomach. You can do a study and, we couldn't confirm that. I bet you couldn't confirm it. And if you treat a rat, published years ago, I'd even forgotten about it. Without soy, they get inflammation, and that's free diet, gets lots of inflammation. Is it bacterial? We don't even know what this inflammation is. It's not exactly prostatitis. And a guy named Angelo DiMarzo came up and found out that proliferative inflammatory atrophy is really the thing that precedes the pen and maybe the culprit. And there's the way I leave you with this, is that the diet is very important. The fat makes the aromatization. The androgens and how they're metabolized to 16 different. The Bukowski and everybody, but androgens and estrogens that are DHT and E will make a tremendous prostate grow. If you get inflammation by imprinting and get oxidative damage, you can change that DNA. These soy gets burned to phytoestrogens and block this by the bacteria in the gut. The burnt meat comes in and superimposes on top of that, and the next thing you know, Cho-En Lai's died of prostate cancer. Dr. Wu did not see much. He trained with Hopkins. So here, how did this happen? It's almost surely that this cancer, this is my lifetime. Look what happened to stomach cancer. It didn't come by sequencing the DNA and coming up with some fancy drug. It came up with the understanding that we didn't even know that when we refrigerated, we're changing Helicobacter. But some of the Helicobacter are beneficial on the esophagus and things. We didn't change this. I don't think Helicobacter do this, do you? Here's smoking. Hell, it wasn't even on the map when I was born. It came after the Second World War. Does smoking cause prostate and breast? No, they go hand in hand. Oh, geez, there's a lot we got to do here. So, folks, I hope we can get the methylation patterns. This area is hypomethylase. That's hyper. The hypermethylation of CpG-alans comes first, then the hypo. I don't know what does that. And then all of a sudden, the SNPs, 5 million difference between you and me. And about 5 of those look like they're important. Then we got some rearrangements and tempers too, and there's a whole bunch of things it hooks up to. And this is a mecca right here of 2 things. Your genetic work And what you all are seeing with your big institute here are some of the best, and they're just like Billy Isaacs is one of the best, and a lot of people, we're learning a ton, okay? Second, we got to learn about those heat shock proteins, and they're the way you have gotten in this room, and the dinosaur didn't make it. Were you tougher than a dinosaur? Well, you must have been. You got here, the dinosaur's gone. Okay, if you want to change it, change the habitat over and over. And the way this system buffers itself with all these things that fold and unfold proteins, and I'm not even going to get into the folding of proteins. It's the next big frontier, I believe. And it's got a lot to do with your heat shocks, where they go, chaperones and stuff. And that's what we're doing up here talking to you. I thank you very much for all this. And that's the way I leave you, to take it home with you. It's late. Let's get out of here and go see the patients, and let's get to the labs and make some more discovery. And Getzenberg and I are honored to be here, and we are here to learn, okay? Not a bunch of fancy dudes coming up from Baltimore who the only urology research department in the country with Hopkins' group for a long time. Now there's a lot of them. So y'all are hooked up with Washington, and there's a lot of interesting stuff going on here between the United States and Canada. And we get through all this money troubles and fighting and killing and torturing people at Guantanamo. Somewhere in here we're going to get this crap straight. Thank you for inviting me here.